Hey, how's it going? This is Ali with TensorFlops, and that's right, we changed the name from the AI Enthusiast to TensorFlops. Today we're going to be talking about the third video, the third topic, which is coding up cross-attention. And so this is again single head self-attention, and let's take a look at the slides real quick. Okay, so you can see here, the first video we covered was cross-attention versus self-attention, talking about the differences. And the second video was then coding up self-attention. Again, this was the single head version. Now in this third video, we're going to be coding up cross-attention. And again, that's going to be the single head version. And then I have decided to make a fourth and a fifth video where I'm going to be doing the multi-head version of both of these attention variations. And I'll be going over also in the future positional embeddings or positional encoding. And so there's many different types. I want to cover the history. I want to talk about what really won out in recent years. But yeah, for today, let's go through cross-attention and coding that up. All right, welcome back. And so, basically in the last section, we did single head self-attention. Now we're just going to do cross-attention. And on the left-hand side, I have the cross-attention, the equations. And the only thing you'll notice the difference between the cross-attention and the self-attention is that we have two sequences. So basically you have, as I was showing in the previous section of the video, you have the input sequence that's basically from the encoder, and then you also have, so this right here, these arrows, and then basically you have the decoder sequence that's flowing up here to the cross-attention module. So let's go ahead and code that up. I'm just going to get started. So we're going to do single cross head attention. And let me see if I can reuse some of my code from upstairs. But before I do that, let's just go ahead and do init, and we'll do self, and then we'll just do, don't forget that we have to do super, and then we have to do init, and then basically we'll do def forward. All right, so there's going to be a lot of inputs, but basically we can get started on the coding side. So on the left-hand side, you can see there's two sequences, XDEC and X encoder. I already mentioned that XDEC it's going to be your batch size by your decoder like time steps and then your embedding dimension. So as already mentioned that your encoder time steps, the number of embeddings you have flowing up over here, does not have to be the same number of embeddings that we have flowing from here. And so that's illustrated in this article here. You can see how this one, this being, it's going to be WQ, so this is going to be the decoder sequence. The decoder sequence has n number of tokens or embeddings, and that ultimately flows through to your attention matrix. You're going to have n, and then you have your second sequence, which is from your encoder, and that you have the K matrix and the V matrix, you generate those. It's going to be M tokens, right? So M tokens from the encoder. And so you have N from the decoder, M from the encoder, and your tension matrix is N by M. And the math works out, the linear algebra works out such that you can do this, and then it will spit out N by dV, right? So your output is going to be the attention vectors, like you've incorporated attention, this attention matrix, and you've taken the value matrix, you've multiplied it out, you get your final vectors, but you have n of them. So n is from your decoder sequence, right? So you're going to have the same number of decoder embeddings as you did flowing up here on the right-hand side. Okay, so we talked about this several times now. Let's just go ahead and jump in and write some code. So on the left-hand side, we have the embedding. And so we're going to do dim encoder. So the encoder has a list of embeddings, and those embeddings are a certain dimension. And likewise, you have embedding dim decoder. Okay. And so attention dim as well. Okay. So this is the output attention dimension. So let's go ahead and do the self.wx or wk equals torch dot torch dot and then dot parameter torch.randn, and that's going to be embedding, if I can type, dim encoder, and that's going to be attention dim. Okay, so that's going to be this guy, and then we have the encoder. And likewise with K, you also have V, so that's going to be the exact same structure. The only thing now different is your Q matrix, and that's not going to be the encoder, that's going to be your decoder. So the dimensions of the input sequence embeddings, right, coming from the decoder side. And then of course we have your self.attention dim is just, your attention dimension. So this is your output, what you're going to be outputting. And let me put this guy up here. And now that's all the things that you got to initialize. Now at forward time, cross attention again takes 2 input sequences. So let's go ahead and do sequence data. Okay, and then we have the encoder sequence data. So on the right-hand or left-hand side, you can see that's this one, and then it's this one. And it's going to be batched by the embedding number of embeddings you have, and then the dimension of the embeddings. You can see here in the equations, we have the exact same dimension coming from the encoder and the decoder. What I'm doing here is a little bit more flexible. I'm saying that the decoder can have its own embedding dimension, and then the encoder can also have its own embedding dimension. And then finally, we already initialized the WQKV dimensions. You can see it's D embed times D attention. So that's these 3 matrices left-hand side. Now we're going to compute the QKV matrices here. You can see here. And so the Q and the K are going to be the decoder, or sorry, the Q itself is just the decoder. K and the V are the encoder, as we've already discussed, I think for like 3 times now. So let's go ahead and let's say, I'm going to say V embeddings. So I'm going to change it up a little bit. See over here. So you have encoder, sequence data. And guys, the reason why I'm typing this is because I want you guys to type with me. Pause the video, keep typing, or see if you understand what's going on, then go ahead and type up the code. It really helps. I will also share this code, right? But like the idea is like, it's always easier to like follow along. I find it easier to learn that way. So anyways, V embeddings, and so we have torch.matmul. I'm going to do the encoder sequence data, and that's just going to be a multiplication with self.wv. And remember, the batch dimension gets ignored. So it's going to be, the output of this is going to be batch size, your time steps, and then of course you have your embedding dim encoder, WV. So it's just going to be output is they're all attention dim, right? So I'm going to copy that over, and then I'm going to do the exact same thing, but I'm going to do that for my K embeddings. And remember, K and V, they're going to use the encoder sequence data. So that's this guy, and then this is going to be K, and then from here QMat, and I could call it QMat, or I could just say Q embeddings if I want, and we'll just do the same exact thing. Well, kind of. So we're just going to do matmul. Instead of the encoder sequence data, we're going to use the decoder sequence data. And you know what? I might as well just rename this decoder sequence data, make it a little bit easier to understand. And you have self.wq. Okay, so you can see here, pretty much just following these equations on the left-hand side. Finally, once you have this, we got to do the attention mat. So let's go ahead and do the next equation, torch.matmul. And we'll do qmat, so the Q matrix, right? And that's going to be embeddings. And then from here, I'm going to do the K embeddings. Okay. And remember, we have to transpose this. And remember, because K embeddings, it is a batch size, time step, attention. We just want to swap the attention dim and the time steps dim. So we're just going to swap -2 and -1. So it's going to become this by this. All right, so now that we're done with that, let's go ahead and continue. We have to scale the attention mat here, so I'm just going to go ahead and do that operation. So you just divide by the square root of your attention dimension. And so we'll do that. And then finally, now that you've done this, you just have to now take the softmax. So we'll do the softmax result. And actually, I think I could just copy this guy over here. I don't have to do much effort there. So it's taking the attention matrix. It's going to do that -1, like we talked about in the last section of the video. And then from there, you do the new embeddings. And this is also going to be pretty much the exact same thing. So I'm just going to do this. And vmat, that was the other, function here. So I'm just going to do v embeddings instead of that, and I should be good to go. Okay, so Softmax result, v embeddings. So you can see how similar it is to the self attention, but the difference here is that we have two sequences, and we just need to mix those in with your K and V matrix. So this is going to be your encoder bit, and then this is going to be your decoder bit. If you do that, you basically did cross attention. And it's very important because, then once you understand cross attention, there's many applications of this. But for now, we coded this up, guys. Congratulations. Tap yourself on the back. Now we're actually just going to have a little bit of a test harness. So let's just say your batch size is 10, your num time steps is 200, your embedding size or dim is 100, and then your attention dim is 10, right? So what we'll do is I actually have the code, but I'll just do self attention, single head, just copy this guy over. I guess not like that. And so we're going to have embedding dim, and that's going to be your embedding dim. And then you have attention dim, and that's going to be your attention dim. Okay, the whole idea here is if you were training the whole transformer model, you have your encoder blocks, you stack them up, right? You have all these encoders stacked together, and then the end encoder, you're going to take the output of that, and you're going to feed that into all of your decoders. So I'm going to replicate that in a very loose fashion here. I have my self-attention, so this is my encoder bit encoder, and so I'm going to feed the output of this to my decoder. And so basically the self-attention, remember the self-attention, this output is going to be your batch size, time steps, and then your embedding dimension, or your attention dim. In this case, the output is going to be by 10. And so then your decoder is just going to take that data. I'm just going to go ahead and copy it in. So you have your cross attention, that's your single cross head attention. We take this guy, and the inputs to this, the encoder dimension, like after you feed the encoder, what is the dimension of an embedding? Well, we specified the output dimension is going to be attention dim. So we're going to put that here. The dimension of a decoder embedding, we'll keep it the same as we saw in these equations, but you could change it if you wanted. And then your attention dim, so like the output vector, so going back to this article, dv, like what do I want my output, like I have n tokens, right? What is my output dimension gonna be? I'm just gonna keep it as attention dim, right? So it's gonna be back to 10. Okay, now we can just go ahead and run this. So I have some sample data, and this is going to be torch.randn. I have my batch size, my num time steps, and my embedding dimension. And so then in my forward pass, so this is like hypothetical, but in my forward pass, this is your block, your declaration of modules or module instances. Then you have the forward. So then you have your data, and then finally you have your forward block, right? And so over here, we can see self-attention. I take the sample data. I have now these embeddings. I pass them in as my encoder sequence data, right? That's the key. And then obviously sequence data, like I'm just going to pass in the sample data. And so we're imagining here that we're looking at the first decoder block. Okay. If we had additional decoders, yeah, then you take the output of that decoder, and that would be the input sequence data. So if you were to stack multiple decoders, and that would be as simple as taking this guy, create another cross attention, and now you're, there you go, pretty much something like that. But now you can see how, one is output, you put that into the other. But yeah, so this is it, guys. Thank you so much for your time. I know this was a long video, but I think these videos are super instructional, and I'm trying to maybe start this type of format. Let me know if you like it. Please like and subscribe. And yeah, see you guys next time. Thank you.